Welcome to Hierarchical EDO, and this is tree data structure. So we will be talking about tree data structure with Swift in this video, and we will be doing multiple operations on Swift, like how do we convert an array into a tree, and then how do we search for a value in a binary search tree, and then how do we do in order, pre-order, or post-order traversal in a binary tree, and then how to get max depth of a tree, how to mirror a tree, and then how to convert a tree into an array. So these are all the questions which you can get in your technical interview, you know. So let's get right into it. Okay, so this is a tree. Yeah, so tree is a hierarchical data structure. So when I say hierarchical, there would be hierarchy. So for example, like your family hierarchy, right? You have great grandfather, then from them you have grandfather, and then from them you have parents, your parents, and then from them you, and then from you you will have children's, right? So tree is exactly like that. So we have nodes, and then this node, the top node is called root node, and then the edge of, we will have child nodes which would be connected to the root node with edges. Okay, so I have given this example of company tree data structure, like company tree hierarchy. So as we know, so in a company, CEO would be at the root node. So he is the boss, right? He is the only one person at the top of the company. So he is the root node, and then under him there will be CTO or CFO, and then in under CTO there will be managers. Under managers we'll have some more hierarchy over here. I have just given this much. So this is an example of tree. Okay, so a tree is nothing but nodes and edges, and it's a hierarchical data structure. And yeah, so we will be talking about this tree today in our code. So I've just written it down over here so that for an easy access while explaining you. And then we will be talking about binary tree. So when we say tree, it can have multiple nodes. So one root node or any node can have multiple child nodes. But when we say binary tree, then it can one node can have only max of two nodes. So either it can have one node or it can have two nodes, but it can never have three nodes. So if in your tree there are three child nodes, then it's not a binary tree. And in your tree all the nodes have maximum of two nodes, then it is a binary tree. So each node can have maximum of two children in a binary tree. And then basically our tree, the one which we will be talking about, will be based on a sorted array. So that's why it is a binary search tree. So binary search tree means all the elements which are uh, uh, all the nodes at the left of the root node will be lesser than the root node, and all the elements, all the nodes at the right of the root node would be greater than the root node. So this is a BST. BST is a short form for binary search tree. So this is a BST because all the nodes at the left of this root node are lesser than this node, and all the elements which are all the nodes which are at the right of this node are greater than this. So that's why it's a BST. Okay, and then I have written some definition for depth and how to get depth and height of the tree, which we will talk when we will go to this operation. Okay, so let's look into our code. So how do you represent a tree data structure in your Swift class, through your Swift class? So as I said, tree is nothing but combination of nodes, and each node will have a value, its left node and its right node. Okay, so left node will represent to the left child node, and right node will represent to the right child node. So node, so one node which has value, so let's say this is our root node value is 8, so value is 8, and left node is 3, so the address of 3 node, and address of 10 node, that is the right node. So this is our first node, so that will be our first node. Okay, and then how do you, the way you initialize in your custom classes in Swift, right? So this is a definition of node through Swift in yeah. Okay, so let's see how do you convert an array. So this is our array, and how do you convert this array into a binary tree? So the way we will do it, we'll create a function which will take array and then first index and last index, and it will return nodes. So as I said, tree is nothing but lot of nodes which are connected with other nodes, right? So one node will be connected with, can have its left node and right node. So yeah, so when we are creating a tree, we have to pass value and then left node and right node. So that's what we'll be doing. So we'll, so to create a binary tree based on an array, we'll be doing it through recursive way. Okay, so for a recursive way, you should have a check which can take you out of that recursive loop. So this is our check. So if our left index is less than first index, sorry, last index is less than first index, then we'll return nil and will not do any operation, will not go to these. Okay, so basically we are saying that once we have traversed through all the indexes in this array, then we'll return nil. If we haven't, then we'll get the mid index of the array, whatever we have passed over here, and then we'll create a node. Okay, so while creating a node, we'll just pass the value of the node. So whatever value we get from the mid element. So this is a sorted array, right? So when we say sorted array, the mid index, the middle element would be the element which will have some value which are less than this and some value which is greater than this. So this would automatically become our root node, right? So root node in binary search tree would be uh, greater than all the elements in the left and all the yeah and lesser than all the elements in the right. So if, with that concept, the middle index for our first array will be our root node, right? And for this root node, left index will pass. So the left index so left index is nothing but the address of the sorry, left node. Okay, so as I said, a tree node is consist of three things: value, so we created the value. Now in this line we are creating the left node, and then in next line we are creating the right node. Okay, so to create the left node, we'll do our recursive call to binary tree itself. Okay, and that will be will pass this array. Our first index would be whatever first index it was, so it would be 0 itself, and last index would be the mid minus 1, right? Because we'll be moving at the left side. So because it's a left node, so mid minus 1. So this will indicate 3, right? So yeah. So no, sorry, this mid minus 1 will indicate 4 over here, right? So our array would be for this array we will be passing first index as this and last index as this. So once this recursive calls comes back over here, we'll have array first index as 0 and last index as 0 1 2 2, right? 2. And then we'll see if this condition is true or not. This will be true. Then we'll come here. Then last index plus first index will become 1. So middle mid index will become 3. So our node would be this 3 array, right? This would become our root node, and then we'll create left and right node for 3. So that will be 2 and so yeah. So again we'll be doing the same thing. So from mid we'll take mid minus 1 for left node, and for from mid again we'll take for right node we'll take mid plus 1. So this recursive loop will make sure that we are creating a binary tree over here, right? So if you, so I will be leaving a link for this code in the description. So I would suggest that you keep some breakpoints, or you can't keep breakpoints playground. So you can put some print statement and see how the recursive statement is, like how the recursion is progressing, so that you can understand how it is working. So basically we are just finding the middle element, and then and then creating our binary tree based on that middle element. So uh, yeah, yeah, so binary search tree, the rule itself says, right? So based on that, we'll create our binary tree. So this will return our root node, and the root node will have left node and right node, as we will assign it over here in these two lines. So these three lines, we are creating our nodes, and each node will be connected through root, left node and right nodes. Cool. Okay, now let's see how it works. So yeah, so this is our over here I have called that function. So binary tree, I'm passing the array which I have created over here. This is the array, and then first index I'm passing as 0, and last index I'm passing as array count minus 1. Okay, and if you see, I have just printed three elements from the tree. The first index, the first tree dot value says the root root of that tree. So the value of the root element is 5, and then value of the left node is 3, and value of the right node is 7. So here 5 3 7. If I say, if I print over here, like let's say if I print in this, if I print left node dot left node, then it should print 2. And sorry, yeah, and the same thing I'll do for right node. Yeah, so if we execute this, then it prints, yeah, it prints 2 2 and 4 for 3. So for 3 our child are 2 and 4, so that's what it's printing, 2 and 4. For 7, the right node, again we can print this the same statement. Instead of left node, we can just say right node, right node. So this should print 6 and 8. Let's see. Yep, exactly correct. Yeah, so this is our whole tree. We don't have to print our tree in such a way. I will show you how to print trees using pre-order and post-order traversal. So how do you traverse the tree? But this is like easy way. Like, I just wanted to show that we have created the tree in such format. So with these line of code, we have successfully created the binary tree based on this array. Okay, now let's say in the same tree which we have created, you want to search for a value. Okay, so over here we are calling this search binary, where we pass our root node tree. So tree will have root node from this binary tree which we have just created the function, and then search value, I want to search for 88. Okay, and I'm getting false from this because in this binary tree I don't have 88. Okay, so how does it work? Let's see. So binary search, as I said, binary search works like every element at the left of the root should be lesser than the root element, and every element at the right of the tree would be greater than the root element. So we will just based on this rule, we will search for our value. So this is our function. This node is root node, and the search value would be the value you want to search. So what you will do is first see if the root node dot value, so this is root node itself, root node dot value is equal to search value. So if that is there, so let's say you want to search for 5, then in that case it will return true. But right now we are searching for 88, right? So it will not return true. Then we'll go over here in this condition. So if search value is less than node dot value, so if search value is less than the root value, then we will perform our search at left side of the root node. In the else condition, we'll perform our search in the right side of the root node. So if search value is less than 5, then we perform our search in this side. If search value is greater than 5, then we perform our search at this side. So our value is greater than 5, that is 88. So we'll be performing over here. So let's say our value was 1. Okay, then we will perform our search in this side. So let's say our value is 1, then it will come in this side of the loop. Okay, and then we'll see if node dot left node is equal to nil. So if our left node is nil, what if this root node doesn't even have a left node? Then in that case we'll return a false, because we couldn't find any element which was matching with search value. Okay, if that is not the case, then we'll do again search binary. Our root node become node dot left node, so we will give this node for search binary. Okay, so we do search binary and then node dot left node, so this would become our root node now. Okay, and then search value will be the same, and then again this function is called. Then we check with node dot value if the value is equals to our search value. So we'll check if 3 is equals to what we have passed. Now our current search value is 1, then it would say, oh no, it's not 1. Then it will, and it is less than node value, then again it will come over here. The left of this is not null, then again will come here, and then this loop will keep on going until we reach this condition. So in this scenario we will reach this condition and we will come out of the loop saying that, okay, sorry, we don't have your element, your search value is not available in this list. Same thing we'll do over here as well. So if the so let's say our search value is 88, which basically we are searching. So we have passed 88 over here. So in that case 88 is greater than uh, root node value, right? Which is root node value is 5, so 88 is obviously greater than 5. So we'll come in this loop. So root node dot node dot right node equals to null. So we'll see if the right node is null. No, it's not null, so we'll come over here. Search binary, we'll send our right node, this node, as root node for search binary, and then search value. Again this the same recursive call will be done, and then we'll again check if the root node, so root node is now this node 7. So we'll see if 7 is equals to 88, it is not. Then we'll come over here. If 7 is if 88 is less than 7, no, it's not. So we'll come over here. So we'll check at the right side. So 7 at the right side of 7 is 8. So we'll search over here. So again this loop will fail because 8 is not equals to 88, and we'll come over here, and we don't have any right node for our node, so we'll basically return false. So 88 is not returned, so that's why we are returning false, because in this array in this tree we don't have 88. Let's say we say 8, we do have 8, so we should get true. Yes, we get true. So as I explained, it will do all the recursive calls, and then at the end it'll say, oh yeah, we have 88, sorry, we have 8, so it's a true, we got the element. Cool. So this is how you do binary search on a tree. Okay, now as I said, you don't have to print a tree like this. If the tree is way too long, then you can't keep saying that root node, then right node, then left node, then value. Oh my god, that would be horrible, right? So how do we print a how do you traverse a tree? So there are different ways of traversing a tree, because you can just go like here, and then you can go like, I will first see this node and 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 this node. So it depends on, like, there are 3 methodologies through which you can traverse a tree. Okay, first is called InOrder Traversal. So that is, you first traverse the left node, and then you traverse the root node, and then you traverse the right node. So you traverse the left node So again, so in these also where you will be giving the root node. Okay, so for the root node you traverse the left node, and then again for this node you traverse the left node. So yeah, so I will give you explanation of how it goes, but yeah, it is. So in order traversal would be left, root, and then right. Pre-order traversal would be root and then left and then right, and post-order traversal will be left, right, and then root. Okay, so in order traversal root would be in the middle. In pre-order traversal root would be at first, and in post-order traversal root would be at the last, and right always goes after left. So left, root, right, root, left, right, and left, right, root. Yeah, that's funny. Okay, so let's see in order traversal, right? So what we do, we have passed the tree root node, and we'll check for root nodes left node. If it is null, if it is not null, then only we'll go inside. If root node next node is, so we'll run this on this, and here is our answer. I'll just increase this. So this is our in order traversal. This is how it prints, and this is our tree. Okay, so what I'm doing is node dot left node. If it is not equals to null, then we do a recursive call to print in order, and then node left dot node, sorry, node dot left node. So we we have given this node in the function, and then we check for left node. If left node is not null, then we pass this function the left node again, and then it will be called again, and then this function again we come here, and we will come over here. So we go through all the left nodes, and once it is equals to null, then we come in this line. So once we are done doing all the left nodes of the root node, then we come over here, this node. So then we'll print the value of 2. So that's why in order traversal the first value is 2. Okay, and then we will be like coming on this line. So node dot right node is not equals to null, but it is a null, so we won't be going anywhere over here. So this left node recursive call will come back, right? So we will go back over here. Now for node 3, we'll print node 3 first. Yeah, and then we will we'll check the right node for this node. So at this time right node is not null, so we will go print in order right node, and this is our 4. So now we are printing 4. So in order traversal will be like this: all the left side elements first, and then root node, and then right node. So we do this check first, and then print our node, and then we do right node check. First left node check, print node, and then right node check. Okay, we'll do this recursive calls for left node and right node, and in the middle root node. We'll be just printing our root node value. Okay, this is in-order traversal. So with in-order traversal, our tree would be printed like 2, 3, 4, 5, 6, 7, 8. So it is like exactly the sorted array. Okay, print pre-order traversal would be, first we will print the root node value itself, then we will do left node recursion, and after that we'll do right node recursion, because it's root, then left, and then right. Okay, so I'm not going to go through with this because you can go through it. So this would be the tree would be printed like 5. So we first print the the root node, and then 3 we first print the root node of this, and then 2 and 4. Similarly 7, then 6 and 8. So this is our pre-order traversal. In post-order traversal we do first we do left node, then right node, and then root node. So first we'll print all the values of this. So 2, 3, 4, then 6, 7, 8, and then 5. So 2, 3, 2, 4, 3, I'm sorry. So left, right, and then root. Okay, left, right, and then root. So 2, 4, 3, and then 5, and oh no, 2 4 3, and then 6 7 8, and then 5. 2 4 3 6 7 8, sorry, 6 8 7 and 5. Oh, okay, yeah. So you do left and then right and then root. So for every child child tree also you will be doing that. So left and then right and then root. So 2 4 3 6 8 7 and then 5. So the same thing, left, do the recursive call for left, and then do the recursive call for right, if the root node right node is there, and then print your value, node value. Okay, cool. So this is how you do in order, pre-order and post order traversals. it's it's very good to know these. It can be asked in many places. Okay. Okay, let's go to our next question. This is very important question, max depth. So how do you define what is max depth of a tree? So for this tree, max depth is 3. How do we get it? So the max depth is the number of nodes to the tree's root node. And there are two definitions of getting the max depth. One is based on nodes and one is based on edges. One is based on these nodes. So depth of this node 4, these the last leaf nodes, would be the number of nodes that have come till the bottom of this last node. So that would be 1 2 3 4. Okay, so depth is 4, whereas height is opposite. So height is like number of nodes till the leaf node. So this itself is leaf node, so that's why height over here is 0. Whereas for the root node, the height is 4, because number of nodes from here till the leaf node is 1 2 3 4. So that's why height is 4, and depth over here is 0, because depth definition is totally opposite, like number of nodes to the tree's root node, and this itself is root node. That's why depth over here is 0. Okay. So what, like, yeah, so you have to count the number of nodes which from the leaf, okay, to get the depth of the node. So the longest path you have to count to get the depth of the node. Okay, so you can't say the depth of this tree is not 1 2 3 based on this. So depth of this node would be 1 2 3 3. Depth of this node is 3, but depth of this tree is the longest path, the number of depth of the longest path leaf node. Okay, so this, these are the last level of this tree. So the depth of these nodes is 4, so that is why the tree depth is 4. So how do we get it? You have to traverse through all the left and right nodes to get the depth of the nodes. Okay, so if root node is nil, then we return. So again, this is through recursive calls. So we will do a recursive call to max depth. So that's why we need a condition through which we can get out of this recursive call. So we will write a condition saying that if root node, so if any node, if we have reached till the condition where root node, whatever we are passing over here, is nil, then we will come out of this loop. Okay, otherwise we'll give if it is not null, then we'll give 0. Okay, so depth of that particular node will be 0 if the if the node is not null. Okay, so this is what this guard statement says. If node is not null, then we return 0. So depth of that particular node would be 0 over here based on this scenario. So what we do, max depth, right? So we'll be storing the depth of each node in this left depth and right depth, and then we'll perform this condition. So if left depth is greater than right depth, because whatever depth is greater, that will in that depth will just add 1. Okay, So let's see. So let's just go through this. So we gave our root node, which is 5. Okay, it is not null. So it is not null. Okay, so that's why will not come into this in this condition. And then we are over here. Yeah, so in this situation we'll just give our root node left node. So we come to this node 3. Then again we run through this. Then our max depth will be we haven't assigned anything in this left depth. And then uh, 3 will be the pointer will come to 2. So root node dot left node, the pointer will become to 2. Okay, so we come over here, root node is not equals to null. We come over here, root node dot left node, again we'll say root node dot left node, where there is no left node. Okay, then it will return 0. Then it will return 0. So left depth, so depth for this particular element is has become 0. Okay, now it comes to this recursive calls. And then we'll do the same thing for the right nodes of this root node. Okay, and then once that is done, we'll see if left depth is greater than right depth. If left depth is greater than right depth, then we'll do left depth plus 1. Okay, so in this particular case left and right would be equal only. So it will come in this in any of these condition, and it will just return it'll just increase the value to plus 1. And then at the end we'll get the number 3. Okay, so this is a binary search tree and it's a balanced tree. That's why so I'm not sure it comes in this loop or this in this condition or this condition, but it will do the same thing. It will keep increasing the count until we reach the so we have traversed till here. Then we'll move back to uh, you know move back to the above levels, and then we'll keep on increasing the depth of the increasing the depth based on our recursive calls. So you can, so I would also suggest, so I what I did to understand is how does it work, the whole how does the recursion flows. I also did wrote some print statement and then see what is being printed afterwards. So that would help a lot. So yeah, so this is how you get the max depth of a tree. Cool. Okay, my charger is very less, so I should charge first. Give me just 1 second. Just quickly put charger. I'm so sorry. Come on, come on, come on, come on. Okay. Okay. Uh-oh. Yeah. Okay, now it's charging. I don't want to cut off in the middle. Cool. Okay, now how to mirror a tree. So mirroring a tree is very simple. So what you have to do is traverse through the left and right of the nodes. Okay, and once you reach at the extreme left and extreme right, you you swap those elements. Sorry, excuse me. So you just swap the left with right and right with left. So in temp we'll take root left node, and then in left node we'll put right node, in right node we'll put temp. So this is the simple swapping mechanism which we do in all our whenever you have to do swapping, right? You just take a temporary variable, you keep the old value in the temp, then swap it be like this. Okay, cool. So this is how we do a mirroring. So you traverse to the left, you traverse to the right, and then you swap it, and then it will go one level above the recursive will go one level above in both left and right, and then we again swap it. So we keep on swapping until the root node is null. Cool. So we'll keep doing this until our root node is null, and then we'll get a mirror tree. Cool. So mirror a tree, I have written, so after mirroring the tree, so yeah, after mirroring the tree also it will be like 537. So if I just print this statement, the whole statement, print, I have just printed three values. So if I print, oops, you can just see the difference between the mirror tree and the normal tree. Yeah, so 578, oh, it's printing the values. So yeah, so left node 5, and then the root node, and then left node is 7. So previously 7 was sorry, right node. Now it is left node. Okay, and then the left node, so 7's left node is 8. Okay, 7's left node is 8. Right now it is right node, so it has become left node, and 7's right node is must be 6. So yeah, so this is correct, right? So we are printing the mirrored tree. So mirroring a tree is very simple. You just have to traverse through left node and traverse through the right node completely traverse through the left node first, and then completely traverse through the right node, and then just print, sorry, and just swap the left node value with the right node. Cool. Okay, the last operation I wanted to do is convert the tree into an array. So that is also again simple task. It is basically it is InOrder Traversal. You do, oh sorry, what is our InOrder Traversal? So InOrder Traversal were left, root, and right. Over here we are doing right, root, and left. Okay, so it's not InOrder Traversal. So yeah, so what you do is you will be calling this uh, function in, so this is again a simple task as we did, right? So we'll first call our right node, and then the append into, so we'll create an array 2. I have created on top itself, yeah, array 2, empty array, and then in this array we'll append the value of the root node. Okay, so as soon every time we do the recursion, we'll just keep on appending the value of the root node and left node and this. So our yeah, so our array comes like 2 3 4 3 5 6 7 8. Yeah, so first go recursive call for right node, then append the value of the node into the array, and then recursive call to the left node. This is how we convert a tree into an array. So this code will convert the tree into an array. So what we are doing, we are just doing three simple things. First, do the recursive call to the right node. So through to all the right nodes, we'll do a recursive call. Then we'll just append the node's value in the array, and then do the recursive call to the left node. Yes. Okay, so this was tree data structure with Swift 4. Thank you so much for watching. If you like this video, please like it and comment it, and please subscribe. Thank you so much. Bye bye.